Okay, so we're going to start on 8.1. This will be kind of just a work section. It's almost like a review of things that you should know. This is what the book expects you to already know by the time you get to 8.1. I don't feel like everything is focused on, so I just want to kind of tell you, I think you guys should absolutely must know how to use sub. Okay, separate the numerator. You must know how to do this. However, you may not always think of it. It may not be the first thing you talk about. For many of you, this is one we're going to learn right now. So you may not know this one. We'll learn this one. Long division. This one's a medium. This one, some of you may know, some of you may not know. But pretty much anytime the numerator has a larger power than the denominator, you probably should try long division if it looks feasible, like it looks like it might help because it might build an easier problem. So this one you probably should know, but not common. Okay, adding and subtracting terms in the numerator, this one is tricky. Okay, you know this one, but it's just kind of weird. I don't know if I'm going to show you one of those, but this is normally a pretty weird one. Hard to kind of identify that one, to be honest with you. Trig identities, must know. So these are things that you should already know. And if you don't, you gotta, when I have some below, you gotta know how to use them. Multiply by 1, you know, but difficult to know when to use. So that's kind of how I feel about these. U sub, you must know. When you see it, you kind of got to know. Separating the numerator, that's normally a pretty common thing. Again, it's not always the first thing people think of, but it kind of helps a lot. Completing the square, probably many of you don't know how to do that. If you had me for Calc 1, I don't think I teach that in Calc 1 because the other schools I teach at, they don't require it. And so I kind of carried that over to Southwestern. So I'm not sure if that's something, I think I might mention it in Calc 1, but it's not something I really focus on. I really focus on U substitution. Long division, you should know, not because it's taught all the time, but you know how to long divide if you're in calculus. You just may not like to do it. Adding, subtract terms, again, we're going to do one of these, I think, and this one's kind of sneaky, and you'll see why. Trig identity, you got to know. That's kind of something that just keeps continuing to come up in this course and in every calculus class you take. Trig is one of those things that it just shows up everywhere. Like you'll be taking some coding theory class and all of a sudden there'll be trigonometry. Or you'll be taking a class on abstract algebra and all of a sudden there'll be a trig problem. There's so much out there that is not pure trig, but it just shows itself in so many different topics in mathematics. That's why you don't really take another trig class after trig, but it just shows up in other classes and you can see what you can do with it. Multiplying by 1. You definitely have been doing this your whole life in math. It's just kind of, it's not easy to identify when it's the right way to go. So we're going to kind of talk about that. These are a few identities that I think you must know from trig. You absolutely must know that sine squared plus cosine squared equals 1, or sine squared theta plus cosine squared theta equals 1. And then if you divide both sides by cosine squared, you would end up with tan squared theta plus 1 equals secant squared. And if you did the Pythagorean identity and divided it by sine squared, you would end up with 1 plus cotangent squared equals cosecant squared. So you can build these identities from scratch. This is like the big one. If you know that one, then you can build this one and you can build that one. Okay. These are the double angle formulas. This one is the most common. I'm just going to tell you right now, this one comes up all the time. That one is constantly coming up in this class. So you should memorize it. Obviously, have it in your notes. This one comes up sometimes, and then these are derived from this one. So you can use the first one. As long as you memorize cosine squared theta minus sine squared theta, you can replace cosine squared with 1 minus sine squared, or you can replace sine squared with 1 minus cosine squared, and you'll get the other two double angles for cosine. So these are a variation of the half angle formula, cosine squared theta and sine squared theta. I sometimes call them power reduction formulas, but I don't know if that's the exact name. It's just how I kind of learned it. Cosine squared theta can be turned into 1 plus cosine 2 theta over 2, and sine squared theta can be turned into 1 minus cosine 2 theta. It's just a variation or a manipulation of the half angle. Notice that both of them use cosine in their answer. It's just the cosine squared becomes a plus and the sine squared becomes a minus. And it's also important to note right here, you guys, if you're using these, that it doubles whatever angle used to be in there, it doubles it. So that's kind of where most people mess up. They make a silly mistake and forget to double whatever angle was in there. So please, when you're doing this, these should be trig identities you have like on a cheat sheet or something that you just know. Like, I know how to use these. I know when I need them. It's something you definitely want to work with. Okay, you guys. So this is where you would pause the video right now. And let's look at number 1. And I want you to pause the video and I want you to see what you got, because this is nothing new that I'm teaching you. This is a problem you already know how to do, but you may not be really sure of it. So I want you to try and then unpause the video and I'll show you how to do it. Okay, so you should have unpaused the video. And I want to know what we're going to use. So we're going to use this, where I'm going to take 4x over x squared plus 9 dx plus the integral of 1 over x squared plus 9 dx. So this is strategy. We are separating numerators, or we're separating the numerator. Okay. So, oops, that's kind of ugly. So our strategy we're using is separating the numerator. And the reason that's kind of cool is right here, when we do that, this is going to become u is equal to x squared plus 9. Oops. Sure. And then du is equal to 2x dx. Divide both sides by 2. So then we have this. Let me actually, I want to write this a little bit smaller, you guys. I kind of am going to run out of room and I don't want to mess everything up. I'm going to do it again the same way, but I just don't want to run out of room. So I can rewrite this as the integral of 4x over x squared plus 9 dx plus the integral of 1 over x squared plus 9 dx. So again, all I did was I split this. I divided that by that and that by that. So I split the numerator into 2 chunks, 4x and 1. And then I divided both of them by x squared plus 9. We know that this can then become the integral, put the 4 in front, of x over x squared plus 9 dx. I'm just a fan of always taking the coefficient or the constant if it's being multiplied or divided. I'm always a fan of just pulling it out of the integral. And this is going to be plus the integral of 1 over x squared plus 9 dx. So now here's the thing. We know that u is equal to x squared plus 9. We know du is equal to 2x dx. Now we'll divide by 2 now that I have a little more room. So now we're going to have 4 over 2 times the integral. Now x dx is worth du. And u, or x squared plus 9, is worth u. Now this one, I actually already know this guy. Does this look familiar from your previous sections you were working on? That should look an awful lot like arctangent, right? That is basically u squared plus a squared, or a squared plus u squared. That's arctan. So we already know that one. We don't have to do anything fancy. That one is just going to be tan inverse of x. However, I think there's a little bit more to, oh yeah, that's if it was just plain old x squared plus 1. So remember, we have to identify that a is worth 3 and u is worth x, right? So then this is actually going to become 1 over 3 times, let me make sure I do this right, x over 3 plus c. So this becomes 2. Now this is actually what du over u is just the natural log of the absolute value of u plus 1/3 tan inverse, or arctan, of x over 3 plus c. And then this is 2 natural log of the absolute value of x squared plus 9 plus 2/3 tan inverse x over 3 plus c. So that's a little bit tougher problem. That's seems sweet and innocent, but that actually required a little bit of effort on our part. I think I have an extra 2 floating around. Oh, yes. So you see right here, you guys, I messed up right here. I should not have put brackets around that. So this will just be 1/3. Yeah, so this 2 right here is only going to this. It's not also going to the other one. I was worried about forgetting to distribute the 2, but it turns out there's not even supposed to be a distribution of 2. Okay, so we just have 2 ln of x squared. Now, I'm just going to tell you guys right now, realistically, I should convert these into parentheses and not into absolute values. Why not? Because it's redundant. Think about it. What's x squared always going to be? X squared is always going to be a positive unless we're dealing with complex numbers or imaginary numbers. So x squared is always going to be a positive, and then you add 9 to it, so you're going to get a positive. When you take a positive plus a positive, you're going to get a positive. So the absolute values are unnecessary in this problem. Okay, so now let's look at this next one. Let's see here. I think we can multiply this one, 5 plus 1 over 5 plus 3 e to the x. Now this one's a little bit tougher one because e to the u are multiplying, doing a u sub won't work. You can't really split it. So this seems a little strange. So what I'm going to try right off the bat is I'm going to try to multiply by e to the negative x. Now, this is a little bit more difficult to come up with. That's hard to, e to the negative x over e to the negative x is actually just 1. But the reason I'm going to do it is I know that whatever I take to be my u, when I differentiate it, I'm going to get du, right? And when you differentiate e to the x, you're just going to get e to the x. So let's see what this does. This is actually, though, kind of one of the stranger problems to just look at it and know. So that's kind of why we're doing this one together. So this would become the integral of e to the over, let's see here. This would be 5e to the negative x. Now this will become plus 3 because e to the negative x times e to the negative x will become e to the 0, and e to the 0 is just 1. So this is dx. So the strategy we're using this time is going to be multiplying by a special 1. Okay. Let's see here. Now we can say let me see, let u equal e to the negative x. So then du will equal negative e to the negative x dx. We're going to divide both sides by -1. So now when we come over here, we're going to have the integral of u over 5u plus 3. And then, oops, that's not u. So what we're going to do is we're going to take this guy right here, e to the negative x, and we're going to replace him with du over -1. So this will become du, oops. And then I'm going to throw the -1 in front there. In reality, some people don't like seeing it like this, so I'll write it like this, 1 over 5u plus 3 du. Some people prefer to see it like that, so I'll write that. Now this would become, now we have to do another u sub. I guess we could call it, I don't know how we say this. It's basically another u sub. Let's see here. I feel like I'm doing something slightly wrong. Oh, you know what I could have done? Yeah, let's go back real quick. I think I could have done a nicer u sub. Because we have a constant in the bottom. I would have basically, I could have done it right now, but I would have ended up doing another u sub. Let's call it an m sub. What I could have done from the beginning is I could have just said, let u equal 5e to the negative x plus 3. Because remember, when we du this is just going to become -5e to the negative x, and then the plus 3 just becomes a 0. So yeah, that'll actually work a lot better, save me a step. So this will become the integral Now I have to divide this by -5 by -5. So this will become -1/5. Now this is gone and this is gone. So I have my e to the -x dx, which matches up there. So that's going to be -1/5 du. So I have my du. And then the denominator is going to be 5e to the -x plus 3 is just u. So then once again, now let me rewrite how I had it. This will be 1 over u du. Some people just prefer to see it that way. So this will be -1/5 ln of the absolute value of u plus c. But that is -1/5 ln of the absolute value of 5e to the -x plus 3 plus c. Okay. So yeah, these are some harder problems. You definitely want to practice the homework that I've listed for 8.1. These problems are going to take a little bit and kind of knock off the rust. This is some integration, and this time you don't know, hey, is this one going to be U sub or not? Like there's a lot of other techniques. Now we're still using U sub all the time, but normally we're using U sub in combination with other techniques. Okay. All right, so let's look at this next one. This next one looks a little bit more straightforward, but not necessarily easier, okay? Now you have x squared over x plus 4 dx. So normally we like to split it, but you can't because it's upside down. It's got the x plus 4 on bottom and the x squared on top. We would prefer it if it was x plus 4 on top in the numerator and x squared in the denominator on bottom, but it's not that way. However, I did say, if we scroll up here, long division. So you should know this guy right here. You should know long division, okay? And you use long division whenever the top power in your expression is bigger than the bottom power. And I shouldn't say always, but it's a good starting point. So what I'm gonna do is I'm gonna do x squared divided by x plus 4. Okay, so now I ask myself the question, what does this guy need to become x squared? Oh, well, he just needs an x, so I'm gonna put an x here, and then I'm going to distribute this to both of those. So this will become x squared plus 4x. Now, the moment I draw the bar, I flip the signs. This goes away, and I'm left with minus 4x. Okay? So this now becomes x minus 4x over x plus 4. Oops, we can go further. I kind of messed that up. Sorry about that. We can go actually a little bit further. I just noticed. Now we have to ask ourselves, what does x plus 4 need to become negative 4x? Okay, so I'm going to say this needs a minus 4, right? So now if I distribute minus 4 times this, I get minus 4x. If I distribute minus 4 times that, I get minus 16. Draw my bar, but the moment you draw the bar, you flip the signs. So this is going to become plus, and this is going to become plus. This is gone, and you now are left with 16. Now I have x minus 4 plus 16 over x plus 4. Looks good. Okay, so hopefully you guys remember how to long divide. I kind of made a silly mistake, but it's normally it only takes one long division to get there, but this is x squared divided by x plus 4, so we still had to go a little bit more. Okay, I'm going to teach you in partial fraction decomposition. You know, there's other ways that we can deal with things like this, but whenever we run into something where the numerator is larger than the denominator in terms of degree, we're normally going to do long division first and then see where we stand. So this means that I now have a new problem to look at. My new problem is going to be the integral of x minus 4 plus 16 over x plus 4 dx. This is my new problem. And then I can integrate this piece by piece, right? So this is going to become x squared over 2 minus 4x plus 16 times the integral of dx over x plus 4. So this one I saved till the end because this one actually requires a little baby u sub x plus 4 du equals dx. So hopefully you guys have done enough of these. So now you can see, let me separate this. So now you can see that this is going to be x squared minus 4x, let's see, plus 16 ln of the absolute value of x plus 4 plus c. So again, once you do enough of these natural logs, you start getting a little bit better at recognizing it. It's a u sub, but it's just a little baby u sub. It's not like a big one. So we have 16 natural log of x plus 4 plus c. All right. I hope you guys have noticed we did u sub in this problem. We did u sub in this problem. We did u sub in this problem. Do you guys see why I told you that you need u sub so greatly? It's an afterthought. The work that we're going on to, u sub is just an afterthought. So we really have to get better at u sub. It just keeps coming up over and over and over again. This isn't really, to me, like one of the crazy strategies. This is more one where you expand the numerator. I don't even know if I listed this one, but I'm just going to FOIL this out. We've been doing this quite a bit in our, when we're doing arc length. So this is going to become 1 plus e to the t, e to the t plus another e to the t would be 2e to the t plus e to the 2t all over e to the 4t. I believe that should be it. Yeah, dt. Okay, so now let's see. If I split this, this becomes 1 over e to the 4t. I think I should be able to integrate that, not too bad, right? You know, I'll write it even better. I'll write it as e to the negative 4t. So now what I'm doing is I'm actually splitting it. I'm saying this one, and this one. I'm splitting it as 3 separate integrals. Plus, dt, plus, now this one will be 2 integral. Now e to the t divided by e to the 4t will become e to the negative 3t dt plus integral. Now e to the 2t divided by, so now I'm doing this one right here, you guys. I'm doing this one. E to the 2t divided by e to the 4t will become e to the negative 2t dt, right? Now, each one of these is going to be a little baby u sub. So this will be u equals negative 4t du equals negative 4 dt. This one will be u equals negative 3t du equals negative 3 dt. And this one is, u equals negative 2t du equals negative 2 dt. Okay. So now when we do our work, we should kind of see that we're going to divide everything by negative 4 here. So this will become negative 1/4. Now it's just going to become e to the u, right? But e to the u is just e to the u, so this will become e to the u. But we know u is negative 4t plus 2 over 3. So this will become minus. Right, all I'm doing is I'm looking at this minus 3 right here. It's going to end up dividing. So this will be e to the negative 3t. And then this will become minus 1/2 e to the negative 2t plus c. So we get negative 1/4 e to the negative 4t, negative 2/3 e to the negative 3t, minus 1/2 e to the negative 2t plus c. So this is, again, not a hard problem, but it definitely takes a minute, okay? So now we have sine squared theta, sine squared 2 theta d theta. So that looks like one of these up here that I asked you guys about. So take a minute, or that I talked to you guys about, use our half angle formula right here. Use our half angle formula for sine squared to adjust this, okay? So pause the video, give it a shot, and then when you unpause it, I'll go over it with you and kind of see if you made the mistake that I see a lot. Okay, so you guys should have done this. You have the integral of 1 minus cosine of 4 theta all over 2 d theta. Now, if you're asking how I got the 4 theta, that means that the problem got you. That's kind of what they're trying to see if you do. Remember, if we go way up here, it says that whatever was in here, you have to double it. So what was in our problem? What was in our problem was a 2 theta. So what would double that be? It would be 4 theta. So that's where I got that from. So now I'm going to split this. This is going to become the integral of 1 over 2 d theta minus 1/2, you know what, I can just write this, I'll split it. 1/2 integral d theta minus 1/2 integral of cosine 4 theta d theta. Do a little u sub right here. U equals 4 theta. du is equal to 4 d theta. Divide both sides by 4. So now we end up with 1/2 theta minus 1/8 integral cosine of u du. But that's going to be 1/2 theta. Don't forget your plus c. I think I forgot it over here somewhere. 1/2 theta minus 1/8. Now the integral of cosine is sine, right? Of and we said u was 4 theta, so sine of 4 theta plus c. So we should get that. Hopefully I didn't mess anything up. Let's see, the integral of cosine would be sine, and then the derivative of that, yep. So that should be okay. I don't actually have that one worked out in front of me on another sheet of paper, so I can't check my answer, but I'm pretty sure that's good. Okay, so now this last one is a newer one. This one is, many of you may never have learned this, so I'm just gonna kind of talk to you about it real quick. This last one is, I guess it's not the last one, but it's the one of the last ones. We're going to use completing the square. So let me see here. I kind of stopped writing the strategies we're using. So this one was multiply by special 1. I think I should have done this. Right. So we should have talked about strategy here. Oops. Let me just kind of fill this in. So this one, the strategy we used was long division. Oops. You know what, maybe I should write it in green. Strategy, long division. That helped in that problem. This one was expanding. I didn't write this as one of the strategies because this one, I mean, I guess it's a strategy, expanding the numerator. But this is a basic strategy that, or a basic technique that you use often. Let's see this next one. Oh, this one was half angle. Okay, and now this one, we need a strategy for this one. So I'm just going to tell you guys right now, this one is a little more difficult. This one is going to be completing the square. And again, I hope you guys are noticing that it's not just about completing the square. It's also, in all of these problems, you normally then have something else to add into it. Okay, so most of these are pretty tough, all right? Now, completing the square in general, in my experience, I have noticed it's pretty difficult. Okay, so what I'm gonna do first is I'm gonna say that U substitution won't work, so I'm gonna throw that out. I can't split this because of the square root. You know, it's not factorable into a perfect square like it was when we worked with those arc length problems. So we're gonna have to try a new strategy. So I'm gonna take this, I'm gonna write negative x squared. You know what, how much room do I have? I'm gonna write it over here. I'm gonna take negative x squared minus 4x plus 1, and I'm gonna complete the square on this. So I'm gonna factor out the negative, and that's gonna give me x squared plus 4x minus 1. Let's see here. So what I'm gonna do is, if you guys remember when you completed the square, normally what you had to do was, let me see here. I'm gonna group these two guys. I'm gonna do it a little bit differently. I'm gonna group these two guys together, and I'm gonna factor out the negative. So this will be negative x squared minus 4x, that's a plus, sorry about that. And then I'm gonna do plus blank plus 1, okay? So this one right here is this one right here. So I haven't changed those. I just kind of left it off on the side, okay? Now, and you'll see why in a second. That's what makes this problem kind of hard. It's a little bit rough. You kind of almost, it's like you have to be looking for it. Now the thing is how would I complete the square on that? Well, remember completing the square. This was something you learned in like algebra and also definitely in pre-calculus. You always look for, once there's a 1 in front of here, you look at this guy right here. Okay, so I'm going to take and I'm going to do 4 divided by 2 squared. That's how you complete the squares. You take b over 2 and you square it. So 4 divided by 2 is 2, squared is 2. Okay. Oops, no, 4 divided by 2 is 2 and 2 squared is 4. I was wondering why it didn't work. So I'm going to put a 4 right there. Okay. X squared. Okay, so I just completed the square. But the problem is I have to remember that whatever I do right here, whatever that is, that's a 4. There was a negative in front. So I just added a -4 to this problem. I just put a -4 in this problem that didn't used to be there. So what I have to do then is I then have to say, well, +4. And that will counterbalance this -4 with a +4. So if I say -4 +4, that means I just added 0. So this is a way you can complete the squared like without changing anything. So now let's look. This will become negative, and then I have x plus 2 squared plus 5. And again, all I'm doing, you guys, is the whole point of completing the square is this problem should now become extremely factorable. It should be a nice, easy problem to factor. Okay, it should be a nice, easy problem to factor because we completed the square. So x plus 2 squared is x plus 2 times x plus 2. If you FOIL that out, you get x squared plus 4x plus 4. Now the thing is, I'm going to put that back in my integral. So this is 1 over the square root of, how do I want to write this? 5 minus x plus 2 quantity squared dx. So just to be clear, all I did was I put this guy right here, and I put this guy right here. So again, understand, I have not changed the problem at all. I took this and I rewrote it as this, and it's still worth the same because I accounted for it. I added a -4 to it, but then I added a +4 to counteract the -4 that I just did. So this is still correct. Okay, now this becomes, well, what does that look like to everybody? Doesn't that look like the arc sine formula where we have our a is equal to the square root of 5 and u is equal to x plus 2, right? And then du is equal to dx, so it works. So this is going to become the integral of 1 over the square root of 5 squared minus, oops, let me write this a little cleaner. I'm running out of room. Sorry about that. 1 over the square root of the square root of 5 squared minus u squared du. Now this looks just like the formula right here and here, where we have a squared minus u squared under a square root. So we know that's arc sine. So this will be arc sine of, and then it says that it's u over a. But in this case, u is x plus 2 and a is square root of 5. So I would say this is one of the hardest problems up until this point in the class. Not because the work was crazy, it's just, it's really hard to recognize that. And then on top of that, to be able to manipulate it and get it to where you want. I just feel like this is a very tough problem, okay? But according to the book, you're already supposed to know how to do this. So don't feel bad if you don't know how to do it. These are basic approaches that you will need moving forward in the class. I don't do completing the square like every, 20 problems. You're not going to see it very often in this course, but it does exist and it's something you have to be aware of. And again, it got us, part of the reason they like to use this is it gets us to our arc sine and our arc tan formulas. Now you just learned inverse sine and inverse tangent. So these are going to kind of be fresh to you. So don't get too frustrated if you're not quite sure of it. Okay. Let me see this last one. Oh, this is another one of the special ones. I added this one because I didn't realize that I had already done a problem with multiplying by 1, but I'll do this one as well. So this one is one of those special cases where we're going to do 1 plus cosine x over 1 plus cosine x. This was oftentimes done in trigonometry whenever you guys were trying to prove an identity in your trig class. Sometimes you had to multiply 1 minus cosine times 1 plus cosine, or you had to multiply 1 minus sine times 1 plus sine. The reason for that is this, from your trig class, you kind of recognize that this a lot of times is going to look like this. It's going to end up as 1 minus cosine squared x dx. Now, the reason that's so good is because when I come over here, we know that this 1 minus cosine squared x is just sine squared x. So this is going to become 1 plus cosine x all over sine squared x dx. Okay. Now we notice that the denominator is a single term, and the numerator has a 1 and plus a cosine, so it's 2 terms. So I'm going to split it like this. I'm going to split it as 2 pieces, and this is going to become the integral of 1 over sine squared x dx plus the integral of cosine x over sine squared x dx. Now you might think that looks terrible, but you know what, I'll put it right here. But this is actually the integral of cosecant squared x dx plus, I'll just write this. We're going to have to do a u sub on this, but I'll just rewrite it for a second. Okay, so now the thing is this is actually an integration formula that you should know from Calc 1. So just think of secant squared. If I asked you for the integral of secant squared, you should say tangent, right? Because the derivative of tangent is secant squared. So remember, whatever you say the antiderivative is, you should be able to then differentiate that and get back to where you started. So what I'm going to do here is I'm going to say cosecant squared x. Well, this has to be cotan, oh, and it's a negative cotan of x. Now this one's going to require a little u sub right here. This is going to be u is equal to sine x, du is equal to cosine x dx. So we have a perfect little u sub. So this is going to become plus the integral of cosine x dx is du over u squared. Okay. So this, so I don't run out of room, negative cotan of x, and then plus the integral of u to the negative 2 du, but this is actually equal to negative cotan of x plus u to the negative 1 over negative 1 plus c, but we know that this is negative cotan of x minus, now remember u we said was sine of x, so this is 1 over sine x plus c. Now if you want, you could get fancy. 1 over sine is cosecant x plus c, right? Pretty sure that's it. That should be the answer right there. Okay, so we have negative cotangent x minus cosecant x plus c. Double check my work, see if there's any mistakes you want to talk to me about. I think everything's fine, but some of these problems I just kind of saw them and I liked them, so I gave them a shot. You know, if there's anything wrong, come talk to me, and it's a good way to work things out, because if I can make a mistake on it, then it maybe will make you feel better that, hey, anybody can mess this up. So feel free to come talk to me about this, but there is a lot of material, I guess, or techniques, and these are all kind of ones that are supposedly you already know according to the book. So give it a shot. Let me know how it works out, and I'll see you guys in class for the next meeting.